All this time talking about ideal gases, and what we've said is that gases are ideal or close to ideal for all gases at room temperature and pressure. So we don't have to think about this too often about what are called real gases. And that's because at STP, standard temperature and pressure, most gases are pretty close to ideal. So the ideal gas, the truly ideal gas, would have a molar volume of 22.41 liters. That's 22.41 liters per mole of gas. And that's what you'd get using the ideal gas law. Now, if you actually do the measurements for, say, chlorine or carbon dioxide or ammonia or any of these gases, you will see that almost all of them are right close to 22.41, helium spot on. Some of them get a little farther away, chlorine, carbon dioxide, but they're all pretty close. And for this course, they're close enough. That's why we use the ideal gas law. But let's think about real gases. And so at low temperatures and high pressures, gases act less ideal. And at low temperatures, the speed of the particles is lower. Therefore, if we think about a collision between two particles, so they're still moving pretty fast, but not as fast as they used to be at higher temperatures. But so when they're moving more slowly, they are close to each other for longer, for a longer time, and attractions between particles that we call intermolecular forces, or IMF, are more important. So we can no longer ignore or neglect intermolecular forces as temperatures go lower. And in fact, as temperatures go lower and lower, the kinetic energy decreases. They go slower and slower until the particles, when they collide, they actually stick and become liquids. So the ultimate non-ideal gas is a liquid. The ultimate non-ideal gas is a liquid, and in the liquid phase and the solid phase beyond that at lower temperatures, intermolecular forces are important. That's what keeps those particles so close together. And at high pressures, the particles are forced closer together so that IMF are important. Remember, our picture of a gas phase is that the gas particles are 10 diameters apart. But at high pressures, those are going to force those particles closer together. They will no longer be 10 diameters apart, and they're close enough together that the volume of the particles becomes significant. And therefore, our picture of an ideal gas as one particle in this entire space is no longer true. Now, they're closer together, so the volume's affected. They're closer together in general, and they're moving more slowly. So intermolecular forces are also important under both of these conditions. So if the question is, when does a gas act non-ideally or as a real gas, you will say at low temperatures and high pressures. Now, there are a number of real gas equations. The one that we're going to talk about in this class is called the Waals equation, and it looks like this. and it says basically pressure times some correction, or sorry, pressure plus some correction, times volume minus some correction equals RT. And what we can do is we can actually reduce this to the ideal gas law. When these two constants, A and B, both equal 0. So when A equals 0, this term drops out and we get just P. When B equals 0, we get V over N. And then the whole thing equals RT. Multiply both sides by N. And you get PV equals nRT. So, and A and B are going to be constants, and those constants are empirically determined, meaning they actually measure pressure, volume, and temperature for gases, and then they fit them to an equation, and they figure out what A and B are.